In this video, we are going to work on problem 3.4.5 from the textbook. Consider a function f from the interval AB to itself, and we assume that f is continuous. In the first part of the problem, we have to prove that the equation f of x equals x has a solution in the interval AB. In the second part of the problem, we impose an additional condition that the absolute value of f of x minus f of y is strictly less than the absolute value of x minus y for all x and y in the interval AB, and x is not equal to y. And then we have to prove that the equation f of x equals x has a unique solution in the interval AB. Now, we are ready to solve the problem. In order to show that there exists some c in the interval AB such that f of c is equal to c, we are going to show that there exists some c in the interval AB such that f of c minus c is equal to 0. So, for convenience, we define the function phi on the interval AB by the following formula. Phi of x is equal to f of x minus x for x in the interval AB. Okay? Then phi is a continuous function. Okay? And let us use the intermediate value theorem. We have the following. Phi of A is equal to f of A minus A. Okay. And as you can see here, f of A is in the interval AB. So f of A is always greater than or equal to A. So this is greater than or equal to 0. And at the same time, phi of B is equal to f of B minus B. And as you can see, because f of B is also in the interval AB, we can see that f of B is always less than or equal to B. So f of B minus B is less than or equal to 0. Okay? So now, if phi of A is equal to 0, or phi of B is equal to 0, then we can see that f of A is equal to A, or f of B is equal to B. Okay. In this case, C is A or C is B. Okay. Now, in the second case, if phi of A is greater than 0 and phi of B is less than 0, by the intermediate value theorem, that is C in the interval AB such that phi of C is equal to 0. So f of C is equal to C. So as you can see here in the equation, f of x equals x always has a solution in the interval AB. Now we are going to work on the second part of the problem. In the second part, we impose an additional condition that the absolute value of f of x minus f of y is strictly less than the absolute value of x minus y whenever x and y are in the interval AB and x is not equal to y. And we are going to show that the equation f of x equals x has a unique solution in the interval AB. Okay, so the strategy is we suppose by contradiction that this equation has two distinct solutions in the interval AB, and then we will show that we can get a contradiction. Okay, so by contradiction, suppose that there exists C1 and C2 in the interval AB, where C1 is not equal to C2, such that f of C1 is equal to C1 and f of C2 is equal to C2. Okay. Then we're going to see that the absolute value of f of C1 minus f of C2 is equal to the absolute value of C1 minus C2. Okay, because as you can see, f of C1 is equal to C1 and f of C2 is equal to C2. Now, because C1 is different from C2, we can apply this inequality and get that this is strictly less than the absolute value of C1 minus C2. Okay, so we can see that over here, the absolute value of C1 minus C2 is strictly less than the absolute value of C1 minus C2. This is a contradiction. Therefore, the equation f of x equals to x has a unique solution in the interval AB.